Welcome everyone to the Outbrief of WP 195324, which was a 2-year program to assess the firefighting capabilities of the commercially available PFAS-free foams and agents. I need to start out by acknowledging the team that helped me perform this program. Starting from the bottom up, the Naval Research Lab, John Farley and Stan Kowalski, who did the firefighting and have been my partners in a lot of these evaluations over the years and provided us the facility to do all the testing. And then I need to acknowledge Dan Martin and Lindsay Hufford for making my job look very easy, and Noah, of course, for helping me with all the environmental aspects. And of course, you guys all know me, I'm responsible for taking credit. From an objective standpoint, ultimately, we'd like to have identified an acceptable PFAS-free AFFF alternative that had the same capabilities as the currently approved mil-spec AFFFs. That wasn't the case, but we do provide an apples-to-apples comparison of the capabilities of commercially available products to mil-spec foams today. We've assessed these capabilities both on an approval and a real scale. We've developed a database of these capabilities that we can use for decision-making processes going forward, and all this will play into the development of the land-based specification. The program had 6 tasks, starting with a literature search to identify the commercially available PFAS-free alternatives for AFFF, a high-level environmental analysis to screen out any non-starters prior to us doing fire testing, 2 scales of fire testing, approval scale as well as representative scale, and some screening of agents in between both of those, and then ultimately developing a final report with recommendations and a database going forward. Our literature search identified 60 to 70 PFAS-free products on the internet that were being marketed as AFFF alternatives. After doing some initial research on that, we determined that about 40 of those had legitimate fire test pedigrees, decent sets of data and approvals to justify them as being legitimate candidates going forward. We have included all 40 of those in our spreadsheet, which links to MSDS sheets/SDS sheets, as well as any approval reports and data that we could find on the various products. We did a very high level screening of those 40 products prior to doing fire testing, and the high level screening was basically looking at the types of compositions or compounds that were listed in the SDS sheets. During that initial screening, we determined there were no obvious showstoppers, so ultimately the selection of products came down to which products had the best fire performance pedigrees, which ones were approved to the toughest standards, which ones had the best fire performance we could find documented throughout the literature. We were originally planning on selecting 10 of those. Going forward, we ended up testing about 25 of those, as well as a number of new formulations being developed by CERTIP and ESTCP. But also a point worth noting here is that the literature review identified, as well as some of the tests that John Farley and the team had done for other commercial organizations, that these are mechanical foams. They don't form a film, so that they're very dependent on foam quality/aspiration. And that directed us a little bit in some of the real scale tests, and I'll explain a little bit more about what I mean by that when we get to that part later. Both the approval scale and the representative scale fire tests were conducted at the Chesapeake Beach detachment of the Naval Research Lab. Here's the aerial view of the site. On the bottom right, you see the burn building, which is where we ran the 28 square foot pan fires. And then the flight deck, which is a 100 by 100 foot concrete pad on the left-hand side, where we ran the real scale tests, as well as we ran the 50 square foot pan fire test that we needed to complete the L curves. And you'll see what I mean by that in a few seconds. We ran approval scale tests based on the 28 square foot pan fire listed in the mil-spec today. It's conducted at 2 gallons a minute of solution flow, AFFF flow, against gasoline, and it's required to be extinguished in 30 seconds. we conducted those tests at 2 and 3 gallons a minute with these available alternatives, and we used both gasoline and Jet A during the tests, separately, obviously. During task 5, we selected the top 7 to go forward into large-scale testing. The large-scale test was 400 square foot pan fire, so it had about a 5-story high flame height, so it's a pretty good sized fire. We fought that fire with a 30-gallon a minute nozzle, and we used it as a standard nozzle, and we also had a foam tube which is designed to aspirate the foam. We ran most of those tests with Jet A, but we did run a couple of them with gasoline. As a point worth noting, 30 gallons a minute against the 400 square foot is the same application rate as 2 gallons a minute against the 28 square foot, so that should give us some decent scaling data. We ran over 100 approval scale tests of commercially available products during this test program. We've also ran a number of new formulations which are not shown in the table on the slide. As you can see in the table, we're using the names of the products. We've gone round and round about whether we wanted to do that, but we've decided ultimately to go ahead and include the names to make the data more useful to DoD. With that said, we are not endorsing or condemning any specific product. We're basically presenting the results as kind of a matter of fact. In the analysis and the discussion going forward, I'm going to talk really about general groupings of performance, not specific products. Okay, so let's talk a little bit about the observations and the results. We need to start off with a discussion of fuel type. As I mentioned previously, we ran both gasoline and Jet A in the 28 square foot pan fires. Now, the fire protection and the hazardous communities in general make a distinction between flammable liquids and combustible liquids. And a flammable liquid is something that has a flash point below 100 degrees F, so it produces a flammable mixture of vapors at the fuel surface at ambient temperature. And combustible liquids have flash points above 100 degrees F and do not produce a flammable mixture of vapors at the fuel surface. And that's what drives the difficulty in extinguishing these fires, because the flammable liquids have a much higher vapor pressure at ambient, as well as after they've been heated by the flame, as compared to combustible liquids. And that's what the obvious first observation we made was that Jet A was significantly easier to put out than gasoline, to the tune of about, the extinguishment times were about half that of gasoline. In addition, gasoline comes in a number of grades as well as a variety of alcohol contents. We typically run the mil spec at 0 alcohol, but you can get E10 winter gas, E15 winter gas, and the addition of alcohol makes it significantly harder to put out. So that's something that needs to be considered going forward when assessing the hazards we're trying to protect. As far as just general results, the AFFF extinguishment times were about half that of the good PFAS-free products. At 2 gallons a minute, AFFF put the Jet A fire out in about 15 seconds, as opposed to 30 seconds for the PFAS-free products. And only about 10% of the products couldn't put that fire out. A 2 gallons a minute solution, which is 0.7 GPM per square foot against the gasoline fire, the AFFF got the fires out in about 30 seconds, and the good PFAS-free products got it out in about 60 seconds, but over 40% of them could not extinguish the fire. As a general ranking of products, AFFF was obviously the best. The PFAS-free foams that were tested like NFPA 11, UL 162, EN 1568, came in second. The wetting agents came in third, and new formulations came in fourth. As alluded to in the previous slide, the gasoline fires were the most challenging, and they provided the best distinction between the higher performance products and the lower performance products. We set the bar initially at 60 seconds extinguishment time with the solution flow rate of 2 gallons a minute. So the spec test fire at 2 gallons a minute with the 60-second extinguishment time. As a refresher, remember that the mil spec requirements are 30 seconds, so a factor of 2 longer. When we set the bar there, 5 products met the requirements. They're the ones that are highlighted in yellow, and that they're the ones that we carried on to do most of the additional testing with. These 5 products have undergone extensive ecotox testing on other CERTIP ESTC programs. And as a final point, 3 of these products are considered Newtonian, so they flow kind of like water or a little thicker than water. And 2 of those are considered non-Newtonian, so they flow more like molasses and or like jello. They're almost a semi-solid. So going into the real scale fire test results, I wanted to show a picture of the size of the fire we were putting out. There's an image of it right there. It's a 400 square foot pan fire. John Farley is the firefighter that suited out that's about to fight the fire, and Stan's the one that's doing the countdown on the right-hand side. We used 150 gallons of fuel during the test. We ran them with both gasoline and Jet A, and that fire burns about 40 gallons of fuel per minute and produces a fire size of about 80 megawatts, which is also about 5 stories tall. During the real scale fire tests, we used 2 discharge devices. We used a standard 30-gallon a minute nozzle shown to the picture on the top right, and the 30-gallon a minute nozzle equipped with a foam tube, which is shown in the picture on the bottom right. When we used the standard nozzle, we determined that the best spray pattern was 15 degrees, and that allowed for a decent reach and the best foam quality we could get out of the nozzle. So at 15 degrees, we got expansion ratios of AFFF in the 5 range, and we had expansion ratios of the fluorine-free foams in the 6 range. When we used the foam tube on the nozzle, the best pattern was a 5-degree spray pattern, which gave us about a 40-foot reach. Happens to be about 40% of the original reach before we put the foam tube on, so we lost some reach capabilities with the tube. But we had very well aspirated foams with AFFF coming in at 18 expansion ratios and fluorine-free foams coming in at about the 22 range. This table summarizes the results of the real scale fire test. As I mentioned, we ran 22 of those. Couple points on the table, and I'll keep it kind of high level description. 2 things, the difference between fuel types. The Jet A was fairly similar to the smaller scale tests, about this, relatively easy, for lack of a better way to describe it, to put out. But the gasoline, on the other hand, was very challenging and was very technique dependent, because the hoses used by manual firefighting, the higher flow rate hoses, tend to plunge and splash the gasoline out of the pan. So it took a little while to develop a technique for the firefighters to be able to fight these fires effectively. So just as a general rule, again, the factor of 2 numbers seem to apply across the board. For the Jet A, without the foam tube, the AFFF put it out in about 45 seconds. The fluorine-free foams had an average of about 60 seconds, so maybe about 1.5, 1.25 there. When we went to the gasoline, the AFFF was able to put it out with the standard nozzle in 50 seconds, but it took 2.5 times that to put it out with the fluorine-free foams with the standard nozzle. They came in at about 135 seconds. But when you add the foam tube, when you get the higher aspiration rates, you get into the 20s expansion ratio range, the times went down by between 30 to 45%, as you can see in the table. So looking at the Jet A with the fluorine-free foams, it went from about a minute to 45 seconds with the addition of the tube, and it went from about a minute 135 seconds to 105 seconds with the tube. So you do get a significant reduction through the use of the foam tube to make better foam quality. But again, as I mentioned earlier, it does reduce your stream reach by about 40%. As another point worth noting, these results didn't necessarily scale well with the smaller scale tests, and I attribute it to edge effects. When you see these fires being extinguished, the center of the fires go out fast, and then you have this edge that you have to build up foam around, because the hot surfaces around the edge tend to relight the fuels, and that seems to be the difference between the smaller scale and the larger scale. You still get the edge effects on the smaller scale, except you can hit the edges from any point in the burn building with the small scale, but in the larger scale, you actually have to run around the pan to actually get to the edges. To analyze these results into a little bit more detail, I have plotted the capabilities of these fluorine-free foams against the legacy AFFF and what I refer to as an L curve. It has the fire extinguishment time on the y-axis and the solution application rate on the x-axis. From a mechanistic standpoint, the shape of the curve makes perfect sense. As you move from left to right, the area on the left side of the plot, the fire is overwhelming the foam, and there's not enough foam being applied to the fire. You get to a point where you start to work your way down the curve where you're providing above the critical application rate of foam to the fire, and you're beginning to reduce the extinguishment times. And then as you move all the way to the far right-hand side of the plot, you get to a point where the foam is being applied well above the rate, the critical rate, so the foam quickly extinguishes the fire, and the addition of more foam doesn't necessarily change the capabilities or the extinguishment times. As a point worth noting, when we test these products, we typically test them around the knee of the curve, and we actually deploy those at the far right-hand side application rates, the 0.1s, the 0.2s, and above. So when we see a lot of failures in the testing, it's because we're at the knee of the curve versus on the far right-hand side of the plot. With respect to the comparison between the fluorine-free foams and the legacy AFFF, the Jet A lines are fairly parallel. The trends are exactly the same, and the critical fire size varies, or critical application rate varies only slightly. Gasoline, on the other hand, as you can see, the blue curve heads toward the infinity much earlier at, say, the 0.05 to 0.04 range, as opposed to gasoline, which then goes to about the 0.02. So the critical application rate for AFFF is much lower, maybe a factor of 2 lower for gasoline than the fluorine-free foams. But above the critical application rates, the lines are fairly parallel, and that the extinguishment times are about a factor of 1.5 to 2 greater than the legacy AFFFs. Okay, as a quick summary, the program started in February 2019. The literature search identified over 60 foams and agents that were being marketed on the internet as PFAS-free or fluorine-free firefighting alternatives to AFFF. 40 of those had legitimate test approval pedigrees, which we included in our database, including the links to MSDS sheets, SDS sheets, test data, things like that. 10 of those were selected for testing. We ended up growing that to over 20 products during the approval scale size tests. We ran 100 approval scale tests during the program and 22 representative scale tests. The tests were conducted with both gasoline and Jet A. The top 5 foams demonstrated good capabilities against all of the fire scenarios we tested and produced extinguishment times that were about 1.5 to 2 times longer than the legacy mil-spec AFFFs. But again, that they were successful against all scenarios. All this being said, I think we may be closer than we originally thought, but time will tell. So from a where we have been to where we're going perspective, the data that we've collected during this program was used to down select the number of agents for testing during WP19 5373, which is a program being conducted by the Naval Research Lab to start the development of the new land-based mil-spec. We will continue to test new products and develop our database even further as things develop in the future. Ansel just released a new product that was UL listed just fairly recently that I'm looking forward to testing down at CBD once things thaw out a little bit. So I'm excited about that. We also have a program, WP19 5374, which is going to assess how foam aspiration / expansion ratio affects the capabilities of these products and compare that to what's being produced by typical DoD hardware. To elaborate a little bit more on that, so we all know these are mechanical foams and they rely heavily on the foam blanket to put out the fire. The L curves that I've shown off to the right-hand side there, the blue line on the L curve was the one we developed for the spec test and has expansions on the order of about 8 to 9. And as the expansion ratio / aspiration is reduced, that L curve is going to shift to the right up that red arrow line, and we're going to determine how far it shifts as a function of foam quality. So we'll develop a series of curves as a function of foam quality for the various products that we're looking at to date. There's another point worth noting that of alcohol content in gasoline is a key variable. Some of my counterparts are learning that the hard way. During a study that we did for NFPA Research Foundation, the Naval Research Lab, and Jensen Hughes did, we determined that E10 gasoline that has 10% alcohol, is about twice as hard to put out as E0 gasoline that has no alcohol in it. So alcohol content is going to be key as a function of whether or not you have to protect that as a hazard or not. There's a couple more points worth noting. So the aspiration, the decrease in capabilities is a function of aspiration, and the decrease in capabilities as a function of alcohol content appears to be product specific. So reducing the aspiration from an 8 to a 5, for example, expansion may affect some foams more than it affects others. So that'll be interesting to learn going forward, and the same kind of thing for alcohol. We also have a test program coming up in China Lake Weapons Center. We're going to run 2 series of tests, one in late April, and then the other series probably in the fall time frame. We're going to go back to China Lake where the original AFFF testing was done back in the late 70s and early 80s and run the debris pile fire test. The debris pile fire is a running fuel fire that flows through a debris field. The fuel is actually heated up by flowing down a series of cascades, then across a giant concrete slab. It's about as representative as you can get as an aircraft crash scenario on the tarmac. I'm looking forward to going back to China Lake. It's been years since I've been there, so that's kind of exciting. And then last but not least, we're going to take all of this data and start to put the pen to the paper to develop the new land-based mil spec going forward. Not knowing whether I needed to cover this or not, this is the expenditures over the course of the 2-year program. The blue line was the planned line, and the orange line is the actual one. To be honest with you, it's better to be lucky than good. Things moved around a lot due to COVID, but the lines pretty much lined up, and we were able to complete the project pretty much on time and under budget. These next 2 slides are to get us all on the same page with respect to what's going on kind of in the commercial side of the house, as well as kind of what the transition plan is going to need to look like for DoD as well. So this is an outline of a roadmap program that I'm involved with NFPA Research Foundation. Robin and Keith are both on the technical panel for that. And these are the topics that we're going to cover in that roadmap. Getting the fire protection, firefighting community up to speed on the current regulations, the health hazards, how to pick a new AFFF alternative, what to do with the old AFFFs, how to clean your equipment, what's acceptable levels, implementation of the new AFFF alternative that you picked, some issues about firefighter exposures, as well as post-fire cleanup. But one of the things I wanted to make kind of everybody aware of is that our industry has always played designer foams. And what I mean by that is that foams are basically tested and formulated for specific hazards. And I'll give you the example. So the aviation DoD industry has always looked for very fast extinguishment and didn't necessarily need a very robust foam blanket. The plan is again, get the fire out as quick as you can, get the people out of the plane, stop the bombs from cooking off. Now the petroleum industry on the other side, which has their own set of standards, they require more of a robust foam blanket, and they don't care that much about fire extinguishment times, or they do, but they don't have the same. They didn't set the bar at the same place that we have as the mil spec in the aviation industry. So when you listen to other people present results, and they use different test methods, and some of them say, well, AFFF mil spec didn't do good on that. That is because it wasn't designed for that. It's not that AFFF's bad, it just really wasn't designed for that. And if you see these guys, these manufacturers all come together, they're always formulating for the particular hazards. So I wanted to close out with a discussion of the development of the land-based mil spec. The focus to date has been on aviation, and that makes perfect sense. First question comes to mind is who's going to do the mil standard 882E evaluation? Keep in mind, this is probably the biggest fire protection decision that the DoD has made in the last 50 years. Probably the previous one was the transition from JP4 to JP5 for aviation fuel back in the late 70s, early 80s time frame. So who's going to do that? And that needs to identify all the use scenarios and what's the max credible event, and where to set the line for performance. Now, the video that you're seeing here is Stan putting out a 400 square foot Jet A fire, so our aviation hazard, maybe one of the MCEs for aviation, with a foam tube adapter on a nozzle, and he's putting it out with one of the top 5 PFAS-free foams at 07 GPM. He gets control in 20 seconds. NFPA 403, which is now 460, which is the commercial standard for ARF. The design basis for AFFF right now in that document is 0.13. So this video is a half of what the design basis is for the industry. And the design basis also includes a 60-second control time. So how good is good enough, right, guys? So I showed the table on the top one more time. Aviation fuel, Jet A is easy because it's a kerosene-based fuel. In fact, 15, 16, 17 products would meet the requirement of control of extinguishment in less than 60 seconds. So ultimately, how good is good enough?